Hello everyone. This presentation is about the operation of the engines on the ground. The presentation deals with the normal procedures of the flight crew operating manual, but does not deal with failure cases. The purpose of this presentation is to provide a set of key messages. These key messages have been defined in order to answer some questions that customers regularly ask, in particular via tech requests. The presentation covers all Airbus aircraft families. This presentation is split into 6 parts. The first part is related to the preliminary cockpit preparation. 3 parts are related to engine start. And the last 2 parts of the presentations are related to the taxi phase. Let's start with the first topic. We'll talk about the check of the engine oil quantity before engine start. Let's explain why a minimum oil quantity is required. The quantity of engine oil needs to compensate for the oil consumption during the flight. The quantity of engine oil needs to remain sufficient at all times in order to correctly lubricate the bearings all along the flight, and it must remain valid regardless of the consumption value. The FCOM procedure takes into account the values for nominal and maximum oil consumption that are declared by the engine manufacturer. The value for maximum oil consumption covers flight operations with one engine inoperative. The quantity of engine oil needs to compensate for the gulp effect during the flight. What is the gulp effect? It can be explained through a chart showing the variation of oil quantity over time. Actually, as soon as engines are running, oil is drawn down from the tank and the oil level is reduced in the tank. This is what we call the gulp effect. There is a transient gulp during engine start, which is quite high. A steady gulp remains when idle is reached. And there is also a transient gulp at takeoff and at go-around. If the oil quantity is not sufficiently high to compensate for the gulp effect, the oil level in the tank may drop down too much and some cockpit effects may be triggered. It could be an oil advisory level on the engine SD page, either related to the quantity or to the pressure, or even an ICAM alert related to the low oil pressure. The quantity of engine oil needs to be checked before each flight. There are 2 objectives. Firstly, it enables the detection of any leak that could appear between the successive flights of a given day of operations. Secondly, it enables to detect any abnormal oil consumption. As a summary, I would say that the minimum engine oil quantity of the flight crew operating manual is defined in order to compensate for the oil consumption and for the gulp effect all along the flight. And this minimum quantity must be checked before each flight. Now, let's talk about the starter limitations. We would like to clarify what we call a start cycle and what we call a start attempt in our flight ops documentation. Actually, one start cycle can include several start attempts. Let's take the example of the LEAP engine on the A320neo. Let's launch an automatic start. If the ignition fails, the FADEC is able to automatically abort the current start attempt and to initiate a new start attempt. It can do it several times. In this example, a start cycle can include up to 3 start attempts. Let's now launch a manual start. For example, let's imagine that an excessive EGT rise is detected. In this example, the flight crew is requested to abort the start. Here, the start cycle includes only one start attempt. We would like to highlight another important point. The flight crew does not need to monitor the running time of the starter. Actually, an ICAM alert is triggered when the maximum running time is reached. This alert is the engine start fault, starter time exceeded, ICAM alert. This alert is active both during automatic and manual engine start. There is one exception, that is the A320 family fitted with IAE engines. Such ICAM alert is not available. However, the FADEC protects the starter during the automatic start because it is able to abort the start when the running limit is reached. As a summary, please remember the difference between what we call a start cycle and what we call a start attempt. And remember also that an ICAM alert is available on the majority of our aircraft to protect the starter and to avoid overshooting the maximum running time. Now I would like to talk about manual engine start. Before that, I would like to remind that the automatic engine start remains the standard start recommended by Airbus for daily operations. The automatic engine start enables to efficiently start engines in most cases. It is fully managed by the FADEC, and it really provides the best compromise between starting performance and engine protection in the overall starting envelope. However, manual engine start can help to start in some specific operational conditions, and I am now going to explain why. The characteristic of manual engine start is to enable to initiate ignition when the maximum motoring speed is reached. The maximum motoring speed provides three advantages. Before ignition, the maximum motoring speed maximizes the torque available to counteract the engine inertia. Before ignition, the maximum motoring speed helps to compensate for low torque generated by the starter. After ignition, to be at the maximum motoring speed minimizes the need to generate some torque via combustion, and this reduces the EGT peak. Due to these characteristics, manual engine start can help to start engines in certain specific operational conditions. In hot or high conditions are critical because they degrade the bleed performance. Manual starts helps to compensate for a low starter torque that results from a low bleed pressure. In hot or high conditions with a deteriorated engine that has a reduced EGT margin, the starting conditions are made critical. The manual engine start helps to minimize the EGT peak. When the performance of the external pneumatic power group is marginal, manual starts helps to compensate for a low starter torque that results from the low air pressure. When some high tailwind is present, manual starts helps to counteract a higher engine inertia due to fan counter rotation. As a summary, I would like to insist on the fact that the manual start may help to start in some adverse operational conditions because it enables the flight crew to set the engine master lever to on at the maximum motoring speed. Now we would like to remind Airbus recommendations regarding the engine start during pushback, especially because some events were reported to Airbus. Some tow bars were damaged, and some aircraft loss of control were experienced. The engine thrust must not be higher than idle thrust. Two facts highlight this statement. The FCOM SOP before pushback or start requests idle to be selected at this stage, and a caution reminds that a hazardous situation may occur if the thrust levers are not set to idle. The tractor weight and the necessary drawbar pull are computed by accounting for idle thrust. The Aircraft Characteristics Manual provides a graph to compute the appropriate towing characteristics. This graph can be retrieved on airbus.com or in a NISI article. As you can see on the graph, the appropriate tractor tow bar weight depends on several parameters, and it is assumed that thrust is set to idle. Crossbleed engine start is not permitted during pushback on A320, A330 and A340 aircraft. During a crossbleed engine start, the engine bleed pressure of the running engine needs to be sufficiently high to start the other engine. On A320, A330 and A340 aircraft, thrust may need to be significantly higher than idle thrust to reach the correct bleed pressure level, and thrust shall not be higher than idle during a pushback maneuver. That's why the FCOM crossbleed engine start procedure was modified in June 2016 to clearly explain that the crossbleed engine start is forbidden during pushback. The objective is to prevent operators from experiencing aircraft control difficulties during a pushback maneuver performed with an engine providing more than idle thrust. As a summary, I would like to repeat that the engine thrust must not be higher than idle during the pushback maneuver. Let's now consider the taxi phase, and let's talk about the engine warm-up at departure and about the engine cooling at arrival. It is very important to comply with the warm-up and cooling times provided in the SOPs of the Flight Crew Operating Manual. First of all, let's have a look at the engine itself. At departure, before takeoff, it is important to comply with the warm-up time in order to ensure a general thermal stabilization of the engine and a correct oil temperature. At arrival, before engine shutdown, it is important to comply with the cooling period in order to avoid the phenomenon of oil and fuel nozzle cocking. This is also necessary to ensure satisfactory temperatures, both temperatures of hot sections and temperatures of cold sections under the colds. It is important to notice that the warm-up and cooling times are recommended by all engine manufacturers in order to reduce long-term engine maintenance costs. The warm-up and cooling times are also required on new engines of new aircraft in order to prevent short-term engine degradation. The warm-up must be performed at idle thrust or near idle thrust. The warm-up starts at engine start when idle is reached. During the taxi-out phase, the normal taxi thrust enables a correct warm-up of the engines. Idle or near idle is appropriate to warm the engines. Takeoff power can be set when the warm-up is complete. The cooling must be performed at idle thrust or near idle thrust. The cooling starts at touchdown. The time spent in approach cannot be taken into account. During the landing roll phase, the maximum reverse thrust is too high to enable a correct cooling of the engine. But the idle reverse thrust is sufficiently low to be taken into account in the cooling period. During the taxi-in phase, the normal taxi thrust enables to correctly cool the engines. Idle or near idle is appropriate to cool the engine. Engine shutdown can be performed when the cooling is complete. As a summary, I would say that the flight crew must comply with the FCOM warm-up and cooling times in order to minimize long-term maintenance costs and in order to avoid short-term engine degradation. Let's finish this presentation by talking about the ice shading procedure on the ground. Ice shading is recommended so as to avoid operational disruption. Why? Because ice can accrete on several parts of the engine in specific weather conditions, mainly on the spinner and on the fan blades, but also within the engine on the core. If this ice accretion is not removed, it can have some adverse effects. Unbalanced deposits of ice can generate engine vibration. Ice ingestion can cause engine damage and progressive engine degradation. Potentially, this may cause thrust loss or engine stall, or an in-flight shutdown in the worst case if the engine degradation is not detected through the engine health monitoring. That's why Airbus recommends that each operator performs ice shading on the ground to minimize the risk of operational disruption that may be induced by ice accretion. Ice shading must be performed when icing conditions are met or if engine vibrations are experienced. The AFM and the FCOM provide the definition of icing conditions. Basically, OAT is at or below 10 degrees Celsius and there is some visible moisture in any form, either in the air or on the ground. Two important remarks. The OAT threshold of 10 degrees Celsius is an envelope value, and some engine manufacturers authorize Airbus to publish a lower value of OAT threshold, 1 degree Celsius for Rolls-Royce and 3 degrees Celsius for Pratt & Whitney and IAE. The freezing fog is a particular case of icing conditions. The freezing fog conditions are announced by the weather reports and by the ATC. A dedicated procedure is available for Rolls-Royce engines. Engine vibrations generally materialize through an increase of V-band1 and are felt in the cockpit. Ice shading must be performed when the time spent in icing conditions has reached a limit. This limit is provided in the AFM and in the FCOM and varies with the engine. The time spent in icing conditions must account for all phases as long as engines are running. The taxi-in, when the aircraft is on hold with engines running, and of course the taxi-out. I would like to insist on the fact that it is important to correctly take into account the time spent in icing conditions during the taxi-in. It is also important to highlight that some ice shading has to be performed just before takeoff, whatever the shading actions previously performed. The flight crew must adapt to the situation each time the ice shading procedure must be applied. As previously explained, the flight crew needs to closely monitor the time spent in icing conditions. Remember that all phases must be accounted for, including the taxi-in phase. Then, the flight crew needs to perform several actions before any ice shading action. Communicate with the airport ground control. Choose a suitable area with a low risk of foreign object damage. Take into account freezing fog conditions that may be reported by the ATC. Take into account the overall traffic on the ground. Apply brakes before thrust increase. And of course, if the aircraft starts to move, immediately set the throttle to idle. And be particularly cautious if the ground surface is slippery. As a summary, I would like to insist on the fact that it is really important to apply the ice shading procedure in order to avoid any operational disruption. As a conclusion, I would say that we have tried to provide through this presentation some responses to several recurrent questions. As a summary, I propose a selection and a repetition of the most important messages. During the preliminary cockpit preparation, check the engine oil quantity before each flight. Regarding engine start, bear in mind three important things. The FADEC generally protects the starter against the maximum starter running time. Manual start increases the possibility to start in adverse operational conditions. And during the pushback, never use more than idle thrust. During taxi, apply warm-up and cooling times to protect the engine, and apply ice shading to avoid operational disruption. Thank you very much for your attention.